Let me just share my screen. Sorry for the delay.
No problem.
How do I share my screen? Share screen. Just a sec. Share screen. Okay. Is my PPT visible?
Yes, ma'am, it's visible.
Okay, fine. Right. So how much time do I have? I think already we are running
You
late.
have 1 hour. You can take. We have a buffer filler time in between the two lectures, so you can take your time, ma'am.
Okay. Okay, fine.
Over to you, ma'am. Thank you.
Okay, thank you. Thank you. All right. So good evening to all the participants. I hope you've all had a good time attending this particular program, this FDP. It has been very useful, I believe. So yesterday we talked about, quickly I'll just go through it right from the beginning so that we are in continuity. Right. So what we did is last time, we just tried to understand what are the basic principles behind genetic algorithms and how we can make use of it by the various just a sec. Oh, it's gone. Sorry about that. Let me just share again. Right. Okay. So what we do is we just looked at the basic idea behind genetic algorithms. And I told you that genetic algorithms is based on the Darwin's theory of evolution. And I told you how one cycle of a GA looks like. And then I told you about the flow chart and how the genetic algorithm is related to the biology of all living organisms. I told you that genetic algorithm is suitable for particularly large-scale problems, NP-hard problems, and complex problems, which cannot be solved using the uh, traditional optimization techniques. I also told you that genetic algorithms are adaptive and they learn from their past experience. And I also told you how the genetic algorithms are different from the traditional algorithms. Then we looked at the main operators which a standardized genetic algorithm has, that is encoding, selection, crossover, mutation, and allopism. We then moved on to the terminology for the various terms that are related to genetic algorithms. The first thing we need to study is the encoding. And as I told you that there are many kinds of encoding. Particularly, we focused on the binary encoding, which means that there is a relationship between the binary numbers and the decimal numbers. So as an example, we took a 4-bit binary string, how it is related to the numeric values. There is a method of converting binary to decimal and vice versa. And similarly, the concept can be extended to a 2-variable problem. And how we can map the lower limit and the upper limit of the binary to the decimal. And that's how we can create a mapping rule, which can take all the points in the domain to the binary space. And this could be done for different variables in a chromosome. And I also showed you about the similar behavior about the octal encoding, the hexadecimal encoding. And I also told you about the specialized kind of encoding, which is called as the permutation encoding, which is a which is a special kind of encoding, particularly used in ordering problems. For example, the traveling salesman problem. And we also looked at value encoding, which is useful for determining the weights of a neural network. I talked about the population size and how to initialize the population. And then we talked about how to evaluate a particular chromosome using the objective function and the fitness. So the fitness function is related to the objective function like this. And then we move to the selection operator. Selection operator is an operator which gives preference to those individuals which have higher fitness. We looked at various kinds of selection operators, and I touched upon the most popular one, that is the tournament selection, where a tournament is played between a pair of chromosomes and the one which is a fitter that goes to the mating pool. Like this, with the help of an example, I showed that if you play a tournament between ith and jth chromosome, then the winner is that individual which has a higher fitness. And it is observed that the individuals which do not have high fitness, they are likely to die. And that is how the resulting population looks like. And we see that an improvement has occurred. Another kind of selection operator is called the Rowland field selection, which is related to the way in which the chromosomes are proportional to the total fitness of the entire population. I think I skipped this last time. Then there is the rank selection, and I've given you an exercise. Then we move to the crossover operator. And I mentioned that although there are numerous crossover operators, I will be touching upon only a couple of them. So first one is the single point crossover. Obviously, the crossover will depend upon the way in which the encoding is defined. If the encoding is in binary, then we do the binary crossover. Otherwise, we need to think of some other ways in which the crossover can be defined. Then we define the double point crossover, the cut and splice crossover, the uniform crossover. And we also define the probability of crossover, which tells us how many individuals of the population should participate in the crossover operator. And we looked at the way in which we could define a procedure for crossover. And then we looked at a couple of examples and saw the actual working. Traveling salesman problem is a problem because it's an ordering problem. So the way in which this crossover will be defined should be slightly different. Then we looked at the way in which mutation is working. And we found that mutation is necessary because if such a situation happens where the entire population has a 0 in the first place, then no matter which crossover you use, you will not reach the minimum. So the advantages of mutation are that it helps to escape local minima and maintains the diversity in the population. We also looked at the various types of mutation, that is the single point mutation and so on. So the single point mutation is very simple. Just randomly choose a mutation site and flip it from 1 to 0 or 0 to 1. And just as we had done for the crossover, exactly in the same manner, we do for the mutation and define the procedure for mutation as follows. Then we looked at some more examples and tried to understand what happens after crossover, and also we looked at the repair mechanism, that is what has been the outcome of the best individual and how to update it. We also looked at elitism. Elitism is a procedure which gives a lot of priority to the best individual in the population. I had given you this exercise, and actually the solution appears over here. So I told you that there are many parameters which are responsible for the performance of a GA, particularly the crossover probability, the mutation probability, length of the chromosome, and the population size. And then I showed you some mathematical examples and showed that if the entire population is generated randomly, then iteration by iteration, they all move to the minimum. This concept can be represented in the form of a convergence graph, where the horizontal axis shows the iteration and the vertical axis shows the objective function value. If instead of the objective function value, you plot the fitness, then instead of going down, this convergence graph will go up. So let's now move on further. I'd given this example. So now let's move on to the application. So some of the applications which me and my group have tried to solve with the help of the genetic algorithms are as follows. So the first one is about the circle packing problem. Now in this problem, suppose you are given an area that has a number of non-overlapping disks which are scattered about its surface as shown below. So this is the given data. So in the given data, you are having a rectangular space which is having a number of circles lying in the entire rectangular region, and these circles are having different center and different radii. Now, the problem lies in the fact that we want to find that circle which is of largest radii, which may be placed among these disks without overlapping any of them. So can you think of a model? You need to define this problem mathematically such that you determine the disk or you determine the circle of the largest area or largest radius, so that it should be placed among the given circles such that they are not overlapping. They are allowed to be tangential, but they are not allowed to be overlapping. So in order to write the mathematical problem, you need to define the objective function. You need to define the givens. you need to define the centers and the radii of the given circles. And you also need to define what are the decision parameters. So the decision parameters are the x and y, the center and the radii of the given circle to be determined. Rest of them are given. And you can model this problem using the optimization problem. But to solve it is not easy analytically. Therefore, we employed the genetic algorithm to solve it. And here is the solution. The solution is the red circle. And as you can see that this red circle is not overlapping any of the given circles, although it is tangential to 3 circles. Okay. Imagine the complexity of the problem if more given circles were present. And imagine the complexity of the problem if this space was too narrow. So therefore, the complexity of the problem plays an important role. The traditional techniques, the analytical techniques are not able to really solve it efficiently. But a genetic algorithm could give the correct result in a couple of iterations. Now the question is, what is the use or what is the role of this circle packing problem in real life? One of my PhD students is currently working on numerous applications of the circle packing problem. But this problem that I'm sharing with you is called the radiation treatment planning problem, which says that we want to expose the affected organ with radiation rays in such a way that the surrounding organs which are at risk are least affected. Okay. So, because you know that whenever there is a terminal disease, that the organ has to be subjected to radiation. And assuming that the radiation shots are in the form of a circle, we need to model this problem as a circle packing problem, and then we can solve it using genetic algorithm. A word of caution is that if the affected organ is to be exposed with radiation, then the surrounding ones should not be exposed to radiation because radiation is harmful. So in order to avoid that situation, the surrounding organs should not be affected, whereas the affected organ should be subjected to the radiation shots. So how to do this? Imagine this is a organ which is affected by the tumor, and it has to be treated with the help of radiation shots. So we'll apply the circle packing problem. That is the first shot. As you can see that the decision of placing the center in the circle at the most appropriate place is not easy, and that's why you need to model it. So this is the first shot that has been applied on this organ. Like this, now we can apply the second shot. And similarly, the third shot. You have to keep on applying 1, 2, 3, 4 like this shots in such a manner that the number of shots should also be minimized. Because every time you are applying a shot, you are subjecting the patient into some kind of a risk. Okay, so therefore, this turns out to be a mixed integer programming problem. That is, the center of the circles and the radii, they are all in real numbers, whereas the number of shots is a positive integer. So the problem turns out to be a mixed integer programming problem. Then we have the fourth shot. And finally, the fifth shot. Now we have applied only 5 shots, but you can see that still some area is uncovered. That is, that area is untreated. But that is coming as not under our control because after all, some error is likely to occur. All right, so second example I want to consider is that of the sine function. Suppose we want to maximize the sine function in the range from 0 to pi. So here this is just a one variable problem, and you can see that the maxima array is achieved at pi by 2, x equal to pi by 2. So that's the way the mapping rule has to be defined. And that's the way the decoded value can be obtained. So let us assume that we have a population of size 4, and we use the roulette wheel selection, and we use the crossover by a single point crossover and a single point mutation. So that's the table that we have. Just a minute. Hello. Actually, I'm in a class. I'll call you later. So the calculations I have done for the first entry, and the similar ones are seen here. Then this is the population which is obtained after the crossover. And you can see I've shown all the calculations. And this is the population after mutation. Therefore, what we find is that the best individual has improved, which is shown in this generation-wise convergence. So suppose the generations are numbered from 0, 1, 2, 3. The best fit and its corresponding fitness are shown. And you can see that the fitness has drastically improved from 0.898 to 0.967 from the 0 to the first generation. And like this, you can complete it. Now, the question is when to stop. So the answer to this is you can specify the fixed number of generations the way you like before starting the algorithm. Okay, then comes the word matching problem. This is an interesting problem which is related to pattern recognition, in the sense that suppose you have a phrase and you want to match the given phrase with your phrase. Okay, you want to match the phrase from a given phrase. So this is just like what the plagiarism softwares do. And also, this problem can be extended to the case of images, to the case of videos, and so on. But just for the sake of illustration, I am showing it for the string. So this is a string, to be or not to be. And if you try to find out the matching, then the total possibilities are as follows: 1 upon 26 to the power 13 in a pure random manner, because there are 13 characters in this phrase. So therefore, the probability to get a correct phase in a pure random manner is 1 upon 26 to the power 13, which is extremely small. Now imagine that this phrase is too small. Suppose the phrase is very large. Suppose you have a text of 100 pages. Then imagine that the complexity of the problem will increase drastically, which means that it is very, very unlikely that the matching will occur. So let's try to solve it using GA. Now, the first thing is the encoding. So what I do is ASCII integers between 97 and 122 are used. So the mapping will be mapping can be defined as the ASCII numbers. A goes to 97, B goes to 98, and so on. And the solution chromosome is to be or not to be. It is 116, that corresponds to T. O corresponds to 111, and like this. So that's the way the encoding has been done. Next comes how to define the fitness. Means how do you know which chromosome is fit and which is not? So therefore, we'll define the fitness as follows: number of places which are matching with the solution. So here is the initial population. I have generated a population of 10 chromosomes, and in the last column I have written the fitness, that is how many individuals are matching with the given chromosome. So to be or not to be was encoded in the right manner, and we find that only 2 places are matching. Same thing will do for the other chromosomes. So that is the way in which the initial population has been generated. Now suppose I use only a mutation with a given probability. Okay, I'm not even using any crossover. I'm just simply using a mutation. Then I can get the optimum result in only 23 generations. And what does this mean? This means that only 230 phrases need to be examined. Okay. So this is a NP-hard problem, which means that if the input size of the problem is large, then the complexity of the problem goes on increasing. Genetic algorithms is particularly suited for these kind of problems. So if I try to record the generation number, the best string, and the fitness, this is what I get. So there you are. At the 23rd generation onwards, I am getting all the bits are matching. In fact, this information I can plot in the form of a convergence graph. If I represent the generation number on the x-axis and the fitness on the vertical axis, then this is the behavior of the objective function of the best chromosome. Like this, the similar problem of text matching, video matching, audio matching can be done very conveniently and in a fair amount of computational time. The fourth example that I want to discuss with you is a combinatorial problem. Remember that combinations play an important role, and the right combination is required for a given scenario. So the design of timetable turns out to be a combinatorial problems where in general there are four main entities: subjects, teachers, locations, and time slots. We want to design the timetable in such a way that all the subjects are taught by some teachers and their location is determined and their time slot is determined. This is a problem which occurs in most of the colleges and schools. And of course, I'm going to consider a simple case, but the generalized version can also be designed. So first thing is that I'm going to take a simplified situation where I'm assuming that the number of teachers is equal to the number of subjects. Means every teacher is going to be given one subject. So suppose this is the data that is there with me. Okay. So let the population size be 30. So we can define the chromosomes as a four tuple, four members, namely subject, teacher, location, and time slots. So for example, 2578 means assign subject 2 to the teacher number 5 at the location number 7 in the time slot 8. So 2578 is a chromosome, and we have identified how we can interpret this chromosome in human beings' language. So next thing is we need to define the fitness. Now, whosoever chromosome does not have any clashes is the best. So therefore, fitness can be defined by the number of clashes. So for clashes, I can impose a punishment value, and that way I can define the total fitness as the sum of all clashes between the subject clash, location clash, and teacher clash. Okay, so that way I can define the fitness. Now, what does it mean by subject clash? Subject clash means when two subjects are allocated at the same time, then that is a clash, and this clash can be dealt with by incrementing the punishment value by unity. Similarly, I can define the location clash where two or more locations are allocated at the same time, and the punishment value is increased by 1. And also the teacher clash where two or more teachers are allocated to a location at the same time, then also the punishment value is increased by 1. So what we have done is we have generated a population and we have defined the fitness. Now we can apply the genetic operators. So tournament selection, single point mutation, single point crossover and mutation. So I can leave this as an exercise for you, and you can see how it works. So there are many applications of genetic algorithm. Just a few of them are listed. Of course, there are a number of books I've already mentioned, and these days you can get this information on the net, no worries. You have the MATLAB code, you have a toolbox on GA in MATLAB. And again, there are so many libraries. So thank you so much for your hearing, and any questions you can ask me. So any questions you can ask me, please. Yeah, so some of you are asking for the material. Yeah, sure, I can share the PPT. No worries about that. There is a question. Why is crossover a part of GA? Wouldn't mutation be enough? That's a good question. Actually, as I said, crossover is an operator which allows to pass the good traits of two or more than two individuals. So that is why crossover is needed. Both the crossover and the mutation, they have their own specific functions. Of course, you can write a GA without a crossover. You can write a GA without a mutation, as I have also shared in some of the examples. It's not necessary to have both. But in general, most of the GAs, they should have both the operators, the crossover and the mutation. What are the real life applications of optimization? Okay, for this I need to give another lecture, maybe for 2-3 hours. You can see my Google Scholar citation, and you will see how we are using optimization to solve real life problems. Particularly, for example, prediction of earthquakes, prediction of avalanche, and similarly, designing of a machine, designing of a vehicle. In fact, any design problem is an optimization problem. So there are many applications. Please see my Google Scholar citation to know. What is vehicle routing problem? Okay, in the context of search algorithm. So vehicle routing is a standardized combinatorial optimization problem where you can, you need to determine which route a particular vehicle should use so that he can reach from the start to the end. So that route optimization is a standardized vehicle routing problem. Why do most of the optimization algorithms take, just a minute, take input as random data? I mean, if I am having a data of 9 by 9 matrix, then I should check each data for more and for maximum and minimum value of the objective function rather than, yeah, sure, you can do that. But you see, the concept of nature-inspired technique is dependent upon a random sample of randomly generated feasible solutions. But sure, if you have such a problem where you are having some data is given to you, you can include that in your population. Okay, let's say you have some experimental data, You can include that into your population. I think in my PPT also I showed you in the beginning. I think I showed you that where I'm saying that initial population. I mentioned over here. Oh dear, where it is gone. I told about the, yeah, here it is. Yeah. So when I said that the population, so for your non-uniformly distributed values, suppose this is the way the population is available, then I can read this from the secondary storage and I can proceed with my GA. That's no worries. So that's an example. Okay. I hope I've answered your question. What is the difference between memetic algorithms and genetic algorithms? I replied to this yesterday also. So memetic algorithms are those genetic algorithms which have local search incorporated into them at certain points, whether it is at the initial population or it is after the individual is obtained after crossover or after mutation. So I would say that memetic algorithms are the generalization of genetic algorithms, where genetic algorithms incorporate the uh, local search into them. Uh, can Markov chain with GA? Yes, you can. Yeah, you can. Sure. What are the advantages of using floating point numbers to represent chromosomes instead of binary numbers? Yes. You see, there is a Hamming cliff problem. The Hamming numbers. Okay, that's a very good question. Actually, because of the nature of integers. So for example, you have 1, you have 10. So let's say you have 0, you have 10, you have 20, you have 30. So these are integers. Okay. Suppose you want some value in between. In order to get a better improved accuracy, you need to have, okay, let me put it this way. Real numbers, they have the property of order denseness, which means that between every two real numbers, there is another real number, right? And again, if you say A and B, then there is a real number between A and B, right? In fact, there are infinitely many real numbers between A and B. Similarly, suppose the real number between A and B is C. Then again, there are infinitely many real numbers between A and C, and like that. This property is called the order denseness property. This doesn't happen in case of binary. So in order that the search space is thoroughly investigated, the use of real coded genetic algorithms is advisable. Okay, and in fact, my as I mentioned yesterday also, my research work is based on the design of new crossover operators and mutation operators for real coded genetic algorithms. Okay, so please go through them and then you will be getting more information about that. Okay, may I try to solve the circle packing problem using other swarm-based algorithms? Is it possible? Where can I find the MATLAB code for this problem? Okay, yes, you can surely solve this circle packing problem with any other nature-inspired technique. Nobody stops you for that. As such, you might not get a ready-made code for this problem at hand, because how many given circles are there cannot be generalized, right? Similarly, the length and breadth of the rectangle, that can also not be generalized. So how you can get a code, ready-made code? You can't get a ready-made code. Okay, you need to model the problem and then you need to solve it using the technique that you are interested in. So you can definitely use any swarm-based technique. You can use Grey Wolf, you can use PSO, you can use ABC, and what all. Sure, you can. Okay. Is the radiation treatment planning problem a part of the circle packing problem, or is it a? You see, the radiation treatment planning problem is the application of circle packing problem. Okay. So I first introduced the circle packing problem, then I showed how the circle packing problem can be used to model the radiation treatment problem. In fact, I mentioned that one of my PhD students currently, he is working on the application of circle packing problems. So one problem he has dealt with is radiation treatment. The other problem is installation of smog-free towers to reduce the pollution. That paper is already published. You can look at my Google Scholar citation. And there's another one that he's doing, rather he did, was installation of mobile towers, the phone mobile towers. These are all applications of circle packing problem. And he has done good work and he's about to submit his thesis. Okay, so there's one more query. The lecture is very interesting. Okay, thank you. I request you to please share the yesterday's session and today's session PPT. Yeah, sure, I will do that. Okay, so that's the last comment. So anybody, any other questions, you are free to ask me.